Recall that previously we defined configuration space and obtained C obstacle and C free for some cases. Next, for motion planning, we consider the robot in any form as a point in C-free. In this lecture, we will talk about how can we represent C-free and search within it for a pass. Here is some advantages and disadvantages of planning for a point robot. The advantage is that planning for a point robot is very efficient, and disadvantages are that this approach needs to transform the obstacles every time the map is updated, and it is very expensive to compute it in higher dimensions. The alternative approach is to plan in the original space, namely the workspace, and only check configurations of interest for collisions. In this course, we use C-space methods for path planning. Why we use this space for path planning? Positions in configuration space tend to be close together for the robot, and it can be easier to solve collision checks and join nearby poses in the configuration space. And this approach allows a level of abstraction that means solution methods can solve a wider range of problems. So next, in this lecture, we will talk about how can we represent C-free and search within it for a pass. Also, continuous representations have some nice mathematical properties. They are not always convenient for representation of C-free. Continuous representations are always convenient, and computers are good and efficient in working with discrete representations. And it is also very common to convert a planning problem to some kind of discrete graph representation, then use one of a variety of existing search algorithms on the graph. So in this course, we will use the discrete state space representations for path planning. There are many methods in the literature for path planning. Here you can see some of them. Complete methods, in which exact representation of the geometry or topology of C-free is performed to ensure completeness. We will define completeness in this course. The other method is grid and graph methods. In these methods, we discretize C-free into a grid and search the grid for a motion from the initial configuration to a grid point in the goal configuration. Sampling methods are based on random or deterministic sampling of C space and then connecting the samples in C-free. Virtual potential fields is another type of motion planning. This is a heuristic approach which is particularly suitable for online planning. And finally, we can formulate the path planning problem as a nonlinear optimization problem and solve it to obtain an optimal path. Let's start with grid and graph based methods. We first talk about some terminology. A graph consists of a collection of nodes n and a collection of edges e. Here you can see the nodes or vertex, and this segment of lines show the edges, and you can see a graph here, and a path can be defined based on these nodes and the edges. So a graph consists of a collection of nodes and a collection of edges, and edges connects two nodes. In motion planning, a node typically represents a configuration or state, while an edge between two nodes indicates the ability to move from one to another one without penetrating an obstacle or violating other constraints. A graph can be weighted or unweighted. In a weighted graph, each edge has a positive cost associated with traversing it. In an unweighted graph, each edge has the same cost. For example, the cost is 1. Thus, the most general type of graph we consider is a weighted graph, and the weights can be determined, for example, based on the distance, the Euclidean distance between two nodes. A graph can be either directed or undirected. In an undirected graph, each edge is bidirectional. If the robot can travel from node A to node B, then it can also travel from B to the node A. In a directed graph, or D graph for short, each edge allows travel in only one direction. The same two nodes can have two edges between them, allowing travel in opposite directions. A tree is also a D graph, the directed graph, in which there are no cycles, and each node has at most one parent node, that is at most one edge leading to the node. A tree has one root and one root node with no parents, and a number of leaves with no child. And here you can see a tree. Given n nodes, any graph can be represented by a matrix A. Its dimension is n by n, in which n is the number of nodes, and the element Aij of the matrix represents the cost or weight of the edge from node I to node j. For example, here you can see a graph and the corresponding matrix. And here A12 is equal to 2. It means that there is an edge between node 1 and node 2, and the weight of this edge is 2. Graph function in MATLAB creates a graph using matrix A, and you see the code here that creates this graph, the graph of previous slide, using this matrix. And here you can see, you can assign the names for the nodes and plot the graph. Dgraph function also creates a directed graph using matrix A, and here you can see another example which creates a directed graph using dgraph function in MATLAB. In this slide, on the left, you can see a semi-free path in which the obstacles can be touched. In some path planning cases, a semi-free path planning is acceptable. On the right, you can see a free path that there is no contact with the obstacles, and the path doesn't touch the boundary of any obstacle. So in this lecture, sometimes we will use semi-free paths to obtain the shortest path for the motion planning. Instead of defining the problem and computing the path specifically for the start and goal configurations, it's more flexible to define a general and compact roadmap, which can be used to plan the path between two arbitrary points. A roadmap, denoted by R, is a graph in C3 in which each vertex is a configuration in C3 and each edge is a collision-free path through C3. In the roadmaps, staying on the road or on the road guarantees avoiding obstacles, and the roads represent effective navigable space. So if we stay on a road, we are sure that we will avoid obstacles. And here you can see a typical roadmap in the presence of obstacles. In graph search, we search the graph for a path from the start to the goal. So this is done after representation of the C3 using a graph. So the graph search is done after representation of the C3 using a graph. One of the most important discrete ways for representation of C3 is using visibility graph. Constructing a roadmap of C3 is complex in general. Some problems admit simple roadmaps. For example, consider a polygonal robot translating among polygonal obstacles in the plane. A suitable roadmap is the weighted undirected visibility graph. So we can obtain a visibility graph for this problem, and then we can use it to obtain a shortest path between two configurations. Visibility graph, also called shortest path roadmap, is obtained with assuming polygonal obstacles in C space. The visibility graph connects all nodes that can see each other. Nodes include start, goal, and all obstacle vertices, as you can see here in this figure. The edges are drawn between all vertices for which the straight line connecting them lies in C3. The obstacle edge also considered in this, in generation of the visibility graph. After obtaining the visibility graph, then a graph search method should be run to find the shortest path between the start and the goal. In this slide, you see a square robot in the workspace with a triangular and a rectangular obstacles. The start and the goal configurations for this square robot or for the reference point are also shown in the workspace. In figure B, you can see the ground C obstacle and you see the C free, the free space. The full visibility graph of this example is shown in figure C, and this graph consists of nodes at the start and the goal configurations. Searching the graph for a shortest path results in a path that you can see in figure B in bold. In figure C, the robot is shown traversing the shortest path. In this lecture, next we will talk about the algorithms to obtain these shortest paths. Here is a theorem about shortest paths. The proof of this theorem can be done easily, and you can see it in the literature. Let's state this theorem. First, two simple definitions. Polygonal path, which is a sequence of connected straight lines, and inner vertex of polygonal path, vertex that is not beginning or the end, is the inner vertex of polygonal path. So if we exclude the last vertex and the first vertex, the rest will be the inner vertex of polygonal path. Let's now state this theorem. Based on this theorem, assuming polygonal obstacles, its shortest path is a polygonal path whose inner vertices are vertices of obstacles. By this theorem, the segments on a shortest path are visibility edges, except for the first and the last segment. To make them visibility edges as well, we add the start and the goal positions as vertices. With this visibility graph as our roadmap, we can now determine the shortest path by some algorithms. There are many algorithms to build visibility graph. In building a visibility graph, inputs are a set of points that define obstacles, and the output is a set of points which correspond to the visibility edges of the obstacles. Here are some algorithms and their computational time complexity. For example, the complexity of the first algorithm is n to the power of 3, in which n is equal to the number of nodes, and you can see the complexity of other methods. For example, in the last one, the complexity is n times log of n plus e, in which the edge is the number of edges in the graph. Here is a sample algorithm for construction of visibility graph. In fact, not all edges are needed in the construction of the graph. In reduced visibility graph, we keep only edges between consecutive reflex vertices and by tangents. Here you can see a visibility graph and the start and the goal node, and here you can see a reduced visibility graph for this problem. You can see the number of edges are much less than this one. So let's define the reflex vertices and bitangents. A vertex of a polygonal obstacle is a reflex if the exterior angle computed in C free is larger than pi. For example, in figure A, you can see that there are 10 reflex vertices for this obstacle, and in figure B you see that there are 9 reflex vertices for this obstacle. A bitangent edge must touch 2 reflex vertices that are mutually visible from each other, and the line must extend outward past each of them without poking into C obstacle. The reduced visibility graph includes edges between consecutive reflex vertices on C obstacle and bitangent edges, and the shortest path in this case is the shortest path between start and goal configuration, as you can see here in this figure. Now let's take a look at pros and cons of visibility graph methods. The visibility graph algorithm is complete. An algorithm is said to be complete if it terminates in finite time with a solution, if such a solution exists, or it will terminate in finite time with an answer of no solution exists. So the visibility graph with this definition is a complete algorithm. The visibility graph approach guarantees existence of shortest path, and it is optimal under the shortest Euclidean path index or metric. And here you can see some cons of visibility graph. It tries to stay as close as possible to obstacles, which is not precisely what we want in practice and in real implementations. Any execution error will lead to a collision complicated in more than 2 dimensions. And this approach solves a subset of the motion planning problem. The assumption of polygonal obstacles is quite restrictive. Note that robot arms and rotation in the plane break the assumptions of polygonal obstacles, and we cannot easily obtain the visibility graph. And for arms, a point obstacle in the workspace becomes a curve in C space. You need explicit access to the polygonal obstacle in C space. That is, you need an explicit definition of C obstacle, which is hard to construct from the obstacles, and these obstacles need to be obstacles need to be polygonal. After computing the visibility graph or a reduced visibility graph of a set of obstacles, we have all we need to compute the shortest path from a start point to the goal point. So we can answer this question. The question is given a representation, a start, a goal, and a motion model. How do we actually generate a plan? The answer is that we can use searching approach to obtain the path. There are many graph search approaches in the literature. For example, BFS, DFS, Dijkstra's algorithm, and A*. In this course, we will introduce Dijkstra's algorithm and A* algorithm, which are the most powerful and popular graph search algorithms. In using these algorithms, we consider some assumptions. Non-holonomic path planning is a difficult problem. So we will start with holonomic robots, and without much loss of generality and performance, we assume to have an omnidirectional or holonomic point robot moving in a workspace or in the configuration space. We also assume that representation of the complex high-dimensional C3 is possible by a one-dimensional roadmap R with these two properties. Reachability, that means from every point Q belongs to C3, a free path to a point Q prime belongs to the roadmap can be found trivially, for example, a straight line path. And the connectivity, that means for each connected component of C3, there is one connected component of roadmap. We also generally consider positive edge weights in graphs. After computing the visibility graph of a set of obstacles, we have all we need to compute the shortest path from a start point to the goal point. Dijkstra's algorithm will now be illustrated using an example. This algorithm, named after its inventor, Edgar Dijkstra, who is one of the founders of computer science. This is just one of his many contributions in computer science. Dijkstra's algorithm is one of the most commonly used path planning algorithms in graph traversal problems. Suppose we have a weighted directed graph. The weights on each edge represent the distance between the two nodes. The problem is here to find the shortest path from S to the G. Shortest is defined as lowest total edge weights. The basic idea of Dijkstra is to explore the vertices of the graph in order of their distance from the starting node and open queue, which are the candidates, the new candidates is ordered according to currently known best cost to arrive. The approach of solving this problem here is greedy approach. The number in the circles will indicate the cost of current shortest path from S to the that node. Initially, we set shortest path cost to 0 for the start vertex because we travel 0 distance to go from S to S, and infinity for the other because no paths have been determined yet. Then the following steps are repeated. Unvisited vertex with lowest cost is selected. Then we'll look at paths to new unvisited nodes. These constitute the open queue set. After that, we update costs if it is lower than a previous cost. We will color as gray the node which shortest distance from S we are currently determining. They are the open queue set. We will also color the nodes that have already been determined as black. We start from the S and consider all edges that go out from S. There are two edges from the S to other nodes. The costs are 5 and 10. Therefore, infinities are replaced by 5 and 10. We choose the lowest of this cost, which is 5. We again consider all the edges that go out of A node. to the other nodes. Here, the cost to arrive to nodes B and C are the same. So we go further and compute the cost to arrive G from these nodes. The cost of the direct pass from A to G is 14, and if the pass goes through B, the cost will be 11, you can see here, and the shortest pass is to go through C, as you can see here, because the total cost will be 8. These nodes are selected. I mean, the nodes C and A and C are selected, and we can finally obtain the red pass that shows the shortest pass from S to G, and the total cost of this pass is 8. We can solve this problem using MATLAB. After forming the weighted graph using dgraph function, we can obtain the shortest pass using the short pass function of the MATLAB. This command is based on Dijkstra's method, and the inputs of this function are the numbers of number of nodes between which the shortest path should be obtained. For example, here nodes we should obtain the shortest path between node 1, which is S, and node number 5, which is node G in our example. This function returns the shortest path, the length of shortest path, as well as the indices of the edges on the shortest path from start to goal that are shown in red in this figure obtained from MATLAB. There are some questions to think about with Dijkstra's method. Would an optimal path ever visit the same node twice? And can there be multiple solutions for the problems like the example we have seen in previous slides? In the next lecture, we will talk about A-star algorithm, which is a graph search method, and then we will discuss other C-free representation and search methods.